Welcome to this explainer. Right out of the gate, we are embarking on a totally mind-bending journey today that is, without a doubt, going to challenge your fundamental intuition about reality. Our goal here isn't just to look at some new abstract physics theory. We're actually going to question the very nature of three-dimensional space itself. If you've ever had that sneaking suspicion that the universe holds secrets way, way stranger than what we can see and touch, well, you are in exactly the right place.
Okay, let's dive into this. I want you to look around the room you're in right now. You perceive height, width, depth, right? You feel like you're moving through a real three-dimensional volume. But what if every single particle, every interaction, and literally every physical event happening inside your room right now is actually completely described by information written on the two-dimensional walls of that room? And I don't mean as a rough approximation. I mean completely and exactly, with absolutely zero information lost. This direct challenge to our perception of physical reality is the beating heart of what theoretical physicists call the holographic principle.
So, to navigate all this heavy physics, here is our roadmap for today. We'll start by exploring the core idea of a 2D reality, tackle the historical black hole crisis, decode the ADS/CFT Rosetta Stone, see exactly how spacetime emerges from quantum entanglement, and finally, look at how scientists are testing all this today. All right, section 1, is reality two-dimensional? Redefining the fundamental nature of space. Now, this brilliantly illustrates the massive difference between an optical illusion and physical reality. On the left, we have a standard optical hologram, where a 2D photographic plate projects a 3D image because it records both light intensity and phase information. The crazy thing is, if you cut that plate in half, the entire 3D image remains because the data is non-locally distributed across the whole thing. But on the right, we have the physical universe. The holographic principle posits a similar non-local distribution of data, but with one monumental difference. The physical reality itself is a lower dimensional boundary theory that completely and exactly encodes a higher dimensional bulk universe. So it's not a trick of the light at all. It's the fundamental architecture of reality. Which brings us to the formal definition. The holographic principle is the conjecture that the complete description of a volume of space is encoded on its boundary surface. And crucially, the degrees of freedom, basically the amount of information, are proportional to the area of that boundary, not the enclosed volume. Think about that for a second. This completely strips away our everyday intuition. It strongly suggests that three-dimensional space isn't actually the primary fundamental reality we think it is. Dimensionality itself might just be an emergent property. Moving to section 2, the black hole area crisis. Thermodynamics breaks the universe. So this whole paradigm shift actually started with a historical mystery back in the 1970s. The great physicist John Archibald Wheeler half-jokingly pointed out a huge universe-breaking problem. He said, if you throw a hot cup of tea into a black hole, the entropy, the overall disorder of the universe seems to just vanish, and that violently violates the second law of thermodynamics. Well, this sparked a rapid, slightly panicked evolution of thought in the physics community. Between 1972 and 1974, Jacob Bekenstein took Wheeler's tea problem very seriously and proposed that black holes must carry their own entropy, localized entirely on their surfaces. Then, right after that, in 1974, Stephen Hawking proved with his now celebrated calculation that black holes aren't totally black. They actually emit thermal radiation. Together, almost by accident, they discovered that the universe stores information on surfaces, not in volumes. So, the crucial point is right here. In normal, everyday physics, entropy scales with volume. If you double the size of a box of gas, you double the maximum possible entropy inside it. Simple, right? But in black hole physics, entropy scales with area. A black hole's entropy is bounded entirely by the 2D surface of its event horizon. Black holes are literally the most information-packed, highly entropic things in the known universe. Yet their maximum capacity doesn't care at all about their volume, it only cares about their surface area. And that area, it is measured in incredibly tiny units, 2.6 times 10 to the negative 70th square meters. I mean, that is an incomprehensibly tiny number. It's called the Planck area, and according to the Bekenstein bound, this is essentially the natural unit of information storage in our universe. You can kind of think of it as a microscopic pixel of reality, with each of these tiny pixels holding exactly one bit of information. Okay, section 3. The ADS/CFT Rosetta Stone, Maldacina's Translation Dictionary. Now, what's really interesting about this slide is how completely different languages can describe the exact same physical theory. Back in the 90s, Juan Maldacena proposed an exact mathematical duality. On one side, you have a string theory with gravity in a higher dimensional bulk space, specifically anti de Sitter, or ADS space. On the other side, you have a conformal field theory, or CFT, completely without gravity, living strictly on its lower dimensional boundary. Just look at this translation dictionary. Gravity and geometry in the bulk literally translate to quantum entanglement on the boundary. The radial depth in the bulk, that translates to the energy scale. A black hole in the bulk is simply a thermal state in the boundary theory. It's a perfect one-to-one Rosetta Stone for physics. The reason this correspondence is an absolute game changer mathematically is because of something called the large N limit. It simplifies incredibly complex, practically impossible to calculate string theory in the bulk into manageable classical supergravity. It literally allows physicists to take terribly hard quantum problems on the boundary and solve them by translating them into much easier classical gravity problems in the bulk. Basically, it took holography from a fun philosophical debate and turned it into a rigorous working mathematical tool.
Section 4. Space-time built from entanglement, solving the information crisis.
Okay, let's look at the notorious black hole information paradox, which is basically the greatest tension in modern physics. Step 1. A pure quantum state, full of highly specific information, falls into a black hole. Step 2. The black hole very slowly evaporates by radiating thermal, featureless Hawking radiation. Step 3. Once the black hole is completely gone, that original information appears permanently lost. But here's the catch. This violently violates a core principle of quantum mechanics called unitarity, which strictly says information can never be destroyed. So how do we possibly resolve this massive breakdown of physics? Well, the answers started to really form back in 2006 with a major breakthrough known as the Ryu-Takayanagi, or RT formula. This formula directly connects quantum information to gravitational geometry. It mathematically states that the quantum entanglement of a boundary region equals the physical area of a minimal surface deep inside the bulk spacetime. This was huge because it strongly suggests that spacetime geometry is actually an emergent property. The physical fabric of space is quite literally woven out of quantum entanglement. Sometimes physicists playfully refer to this as the it from qubit perspective.
Building on that, Maldacena and Susskind proposed the ER-EPR conjecture. This basically suggests that anytime two particles are quantumly entangled, which is the EPR part, they are actually physically connected by a tiny geometric wormhole, which is the ER part. And more recently, physicists developed what's called the island formula. It shows that when you calculate the entropy of Hawking radiation, you have to include a hidden island connected by a wormhole deep inside the black hole interior. And you know what? When you do the math, the information isn't lost at all. It perfectly recovers what's called the page curve, entirely saving quantum unitarity. The boundary description is complete, and the information is perfectly preserved. Crisis averted.
All right, our final section, Section 5, testing the holographic universe, from abstract math to real-world physics.
Believe it or not, this incredibly abstract string theory math is being used right now to model complex terrestrial quantum systems where our standard methods just completely fail. Physicists use it to understand strange metals. These are bizarre materials that totally defy conventional electron behavior. They've built holographic superconductors that successfully model the spontaneous condensation and the expulsion of magnetic fields. And maybe most impressively, they've used it to study quark-gluon plasmas created in ultra-relativistic heavy ion collisions. Let's move to and see how this builds in a real experiment. When scientists smashed heavy ions together to create a quark-gluon plasma, standard physics estimates predicted a highly viscous fluid. But the holographic model? It predicted the exact opposite, an incredibly low viscosity, a universal lower bound for near-perfect fluids. And when they actually measured the plasma at the relativistic heavy ion collider, no way, the result matched the holographic prediction almost perfectly. It was a massive, unexpected victory for ADS/CFT applied to a real physical system. And, the work literally hasn't stopped. The very latest state-of-the-art research from 2025 by Varela, Katyal, and Bhattacharya pushes this paradigm even further. Because direct physical experiments on quantum gravity would require energies billions of times higher than what our current particle accelerators can produce, these researchers use the holographic principle as a precision mathematical apparatus. The math itself has effectively become the experimental instrument, probing the fundamental structure of a complete theory of quantum gravity,
all from the safety of the theoretical boundary. So we've gone from the thermodynamic puzzles of black holes swallowing cups of tea to the mind-blowing idea that the entire universe might just be a two-dimensional boundary projecting a three-dimensional illusion woven entirely out of quantum entanglement. Which leaves us with a truly mind-bending philosophical question to end on. If three-dimensional space is ultimately an emergent holographic illusion, what does that mean for the concept of where you are right now? Think about that the next time you look at the walls of your room. Thanks for exploring with us.